Can everyone hear me? Today I will give you tutorial 1, and first I will introduce who I am. I'm Ling Rui, and you can call me Ray. If you have any questions, you can contact me by sending me emails. Or if you would like to talk to me face-to-face, you can come to my office. But before you come to my office, please send me an email to tell me when will you come and what questions you have. By doing this, it will save us a lot of time. And by the way, the questions of tutorial 1 is set by another tutor Liu Chang. So if you have any questions, you can also send him email to ask for help. I will begin the tutorial soon. And if you have any questions, you can unmute your microphone to stop me directly. Or you can tap your questions on the screen. Once I say it, I will stop and illustrate questions. But some questions is time consuming to illustrate it during the tutorial. So if we meet that case, I will ask you to type your emails on the screen. I will contact you personally after the tutorial. Now we begin our tutorial. We come to the question 1. For question 1, we talk about matrix addition. For matrix addition, we have 3 key points. The first point is that the dimensions of addends must match. And the second point is that when we perform the matrix addition, we should perform it element-wise addition. And the third point is that when there is a scalar and we need to do the multiplication, we do the multiplication with each element. As you can see, we have 3 questions. In question 1, we will use each question to illustrate one key point. Now we move to the next page. We focus on question A first. For question A, as we mentioned before, we will check the size. The size of the first matrix is 3 times 2. And the size of the second matrix is 3 times 3. So it's obvious that these 2 matrices do not have the same dimensions. According to the key point 1, these 2 matrices cannot do the matrix addition. And now we move to the question B. For question B, we check the size first too. The size of the first matrix is 3 times 3, and the size of the second matrix is 3 times 3 as well. So according to the key point 1, we can know that we can do the matrix addition. Now we are going to see what does element-wise addition mean. Now we see these 2 elements. These 2 elements are at the same position. So we add these 2 elements together to get the answer 3. And then we move to this element. 2 and 1 are at the same position. So we add these 2 elements together and get the answer 3. And I think you already know what does element-wise mean and think it is very easy. So we just take one more example. For example, this element 9 and element 3 are at the same position. So we put them together to get the answer 12. So by solving question B, I think you already learn how to do the matrix addition by element-wise way. The students in the last tutorial have a question that whether we can skip this step. Actually, yes, since I show the details because I want you to know what does element-wise mean. Once you are very familiar with the calculation, you can directly get the answer at the right side. And now we move to question C. Question C, we can see there is a scalar. So we need to do the multiplication between the scalar and the matrix. As we mentioned before, in the third point, we should do the multiplication between the elements and every element in the matrix. So please focus on this part. We can see there is a scalar and there is a matrix. So according to the point 3, we times 3 and 2, 3 and 1, 3 and 0, 3 and 0, 3 and 1, 3 and 1. Then we get the answer like 6, 3, 0, 0, 3, 3, and 3, 0, 9. So by doing this, you already know what that means. When we have a scalar and when we have a matrix, we need to do the multiplication between the scalar and every element in the matrix. And now we move to the next step. We should do the element-wise addition. That means we use 2 to minus 6 and 0 to minus 3 and 4 to minus 0. So in this way, we can get the final answer. I think matrix addition is very easy to follow. And now we already know what should we pay attention to when we do matrix addition. The 3 key point is check the dimension first, then do the element-wise addition. And third, if we meet a scalar, we should do the multiplication between the scalar and every element in the matrix. Now, I think you may not have questions for question 1 because it's very easy. So I move to question 2 directly. For question 2, we talk about matrix multiplication. For matrix multiplication, we also have 3 key points. The first key point is that we should check the dimension of the operands and they must fit. For example, there is a matrix of size n times n. That means this matrix have n rows and m columns. And then we have another matrix m times p. That means this matrix have m rows and p columns. The point 1 tells us the number of the columns of the first matrix should be exactly the same as the number of rows of the second matrix. If this condition is not satisfied, there is no necessary to do the matrix multiplication since it is impossible. Then we are going to see the second point. The second point tells us the final results will be of the size n times p. We can find that the number of rows of the final result is the same as the number of rows of the first matrix. The number of columns of the final result is the same as the number of the columns of the second matrix. So after we learn the first point and the second point, we already know how to decide whether these two matrices are possible to do the multiplication, and we can also do a prediction about the final size of the result. And we can also check whether we do the calculation right or not. If you do the calculation wrong, you are possible to have the wrong size of the final result. And the key point 3, it tells us how to do the calculation. It says the result element is the dot product of corresponding row and column. I will illustrate it by solving the questions in question 2. So next page, we will see how to use these 3 key points. First, we are going to see question A. Again, we should check the size. The first matrix is of size 3 times 2, and the second matrix is of size 3 times 3. It's obvious that the number of the columns of the first matrix is not the same as the number of rows of the second matrix. So we already know there is no necessary to do the calculation because it's not possible. Then we move to question B. For question B, we need to check the size first. It's of size 3 times 3, 3 times 3. So you can see these two are the same. So they can do the calculation. And now we are going to see how we do the calculation exactly. Now we already have the answer. And this matrix is of size 3 times 3. We can use the key point 2 to check whether the answer is of the same, is of the right shape. We can see this is 3 and this is 3. So the shape is correct. Now we are going to see how we do the calculation. For the sake of simplicity, I use another notation to denote the matrix. It's A11, A12, A13, and A21, A22, A23. The third row is A31, A32, and A33. The footnote of the notation means the position. For example, A11 means this element is at the first row and the first column. And for this element is at the position of the second row, the third column. Now we are going to see how we use the footnote to do the calculation. We take this element as example. It is of the position 1, 1. So we find the first row of this matrix and the first column of the second matrix, and the 5 is calculated by 1 times 2, add 2 times 0, add 3 times 1. So this is 5. Then we take this element as an example. This element is of position 2, 3. So we take the second row and the third column. And 23 is calculated by 4 times 0, add 5 times 1, add 6 times 3. So we get 23 here. And now I think you already understand what does the key point 3 says. It says the element result is the dot product of the corresponding row and the columns. So actually, when we want to calculate the elements, we just need to find out the position. Then we use the position to find the corresponding row and the corresponding columns and do the dot product. And finally, we can get the answer. It's very easy, right? Then we come to the question C. For question C, again, we check the size. It's 4 times 1, and it's 1 times 4. And then we make a prediction. The size of the final results must be 4 times 4. And now we see the solution. We take this element as an example. It's of position 1, 1. So we find the first row and the first column. So we get 0 times 0 is still equal to 0. And we randomly found another example. How about this? Its position is 4, 3. So we find the fourth row and the third column, and is calculated by 4 times 3. So in this way, we can calculate out each element in the final matrix. So that's the way we do the calculation of matrix multiplication. And for the question D, the size is 1 times 4 and 4 times 1. So we can already know the final answer is a matrix of size 1 times 1. So it's actually a scalar. And this is the solution. Actually, there is only one row and only one column. So we just do the dot product. 9 is calculated by 0 times 0 1 times 3, 3 times 2, and 0 times 4. So the result is 9. You can see that question C and question D seems kind of strange, but after we check the dimensions, they truly can do the matrix multiplication. And for question 2, I hope you have already bear in mind that we still have 3 key points. First, check the dimensions, whether these two matrices can do the matrix multiplication. Then we can predict the size of the final matrix to check whether we do the calculation right. Then the final step is we should find the corresponding rows and the corresponding columns to do the calculation correctly. Does anyone have questions? If you have questions, you can type it on the screen or unmute your microphone. If not, I will move to question 3. Well, no one have questions, right? I will move to question 3.
Excuse me, I would like to ask something about the question 2. There are also 2 more questions, and where can we find the answer of it? Thank you.
After the tutorial, we will post the answers on the Moodle, so you can check the answers on the Moodle. And now we move to question 3. For question 3, we still talk about matrix multiplication, but this time it has something special. First, we focus on question A and question B, and we can find that there are 2 matrices look like this. They only have element 1, and the element 1 only appears on the diagonal. And for this kind of question, and for this kind of matrices, we call it identity matrix. You can see this in the key point. And when we meet this kind of matrix in the matrix multiplication, there is no necessary for us to do the regular calculation. We can get the correct answer directly, as shown here. I means the identity matrix. No matter the identity matrix appears at the left side of A or the right side of A, the final answer is always A. Now we are going to check and verify whether this key point tells us the truth. So we go to the next page. On this page, we are going to see question A and B. We denote this matrix as A, this matrix as I, this matrix is I, and this matrix is A. And in the last tutorial, some students have the question that if we have 2 matrices A and B, and it's possible for them to do the calculation AB and BA. Is AB and BA the same? And the answer is this is not always true, but if one of them is the identity matrix, then the conclusion is true. We will see this in this page and the next page. So let's do the calculation first. For the question A, first we do the regular calculation. We use the first row to time the first column to get 6, and first row to time the second row to get the element 2. So step by step, we can get the final answer. We denote it as C1. And actually, it's the same for question B. For question B, the identity matrix is on the left side. So we use the row of the identity matrix to time the column of the matrix A. And step by step, we can get the final answer and denote it as C2. After doing the calculation, we can find that AI is equal to IA is equal to C1 is equal to C2. And in this case, it seems that this conclusion is correct. but that's because one of these two matrices are identity matrix. And now we move to the next page to see in general case why this conclusion is not correct. On this page, we focus on question C and question D. For question C and D, we can see there seems to be two special matrices as well. These two matrices also only contain element 1. However, the elements are not on the diagonal. So these two matrices are not identity matrix. However, when a matrix do matrix multiplication with this kind of matrices, they still have something special, and we will see it in the solution. First, we calculate AB. First, we do it in a regular way. We use the first row to time the first column, the first row, the second column, the first row, the third column, to get the final matrix, and we denote it as C1 as well. And now we compare the matrix C1 and matrix A. We can see that it seems after the matrix multiplication, we only change the positions of the columns, and it seems that the positions of the columns is close related to the position of the element 1. And now we are going to see what's the relationship between the position of 1 and the position of the columns. We start with the green element 1. Its position is 3, 1. And we can see that the third column in matrix A becomes the first column in matrix C1. And next, we go to the red element 1 is at the position 1, 2. We can see that the first column of matrix A becomes the second column of matrix C1. And last, we go to the blue element 1. It's at the position 2, 3. We can see that it changed the second column of the matrix A to the third column of matrix C1. So I think you already get the rule of how the special matrix change the positions of the columns of A. But actually it's the concept under here. You can see there is a concept called matrix transformation. This is only a very special case, but I hope you can get a feeling of the matrix transformation. And I think Dr. Wang will tell you more about this. And now we go to question D. For question D, the special matrix B is on the left side of A. And at the beginning, we also do the regular calculation. We use the first row to time the first column, the first row to time the second, and the first row to time the third column. And finally, we get the result C2. And now we compare the result C2 to matrix 1. We can observe that it seems that at this time, we only change the position of the rows of the matrix A. And again, it seems closely related to the position of the element 1 in the special matrix B. Again, we start from this element 1. Its position is 3, 1. And we can see that its first row now becomes the third row of C2. And its position is 1, 2. And we can find that the second row of the matrix A now becomes the first row of matrix C2. And for this green element 1, its position is 2, 3. And we can find that the third row of matrix A now become the second row of matrix C2. Now, I think you got the rows already. So I think you can bear in mind that if you meet the questions that want to do the matrix multiplication and appears the special matrices looks like this, you can use the rows we found today to get the answer instead of doing the regular calculation. Actually is the topic under the matrix transformation. I can give you a very simple conclusion, but more details will need you to find yourself or learn from Dr. Wang. So the summary is like this. When we have a matrix A and have another and have a matrix B, if we put the matrix B on the right side of the matrix A, we actually change the columns of A. And if we put the matrix B on the left side of A, we actually change the rows of matrix A. I think you will learn it later, so you can just bear this simple summary in mind. Now, and the key point is that you get a feeling about this. Now we move to question 4. Does anyone have question? If you have, don't be shy to unmute your microphone or type your questions on the screen. Or I will move to question 4. Now for question 4, in question 4, we are going to talk about the properties. I will not spend much time in this topic because I think it's very intuitive. I will spend a very short time to explain this. For example, this is a matrix A, and this is a matrix B, and this is a matrix C. And in question A, it's actually asks, we do the A times B first, then use C to time the matrix we get before. And in question B, actually we calculate B and C first, then use A to time them. So we are going to check whether these two are the same. We go to the next page to see more details. We can see that I think the derivation is quite easy. So though it looks kind of complex, but we can do it step by step. First, we do A times B first. So we use the first row to time the first column, and the first row to time the second column. So we can get this matrix. Then we use matrix C to do multiplication with this matrix. And we can get the answer by use the first row of the big matrix to time the first column of C. Then first row to time the second column of C. Then we can get this huge matrix, and we denote it as D1. And now we move to question B. For question B, we need to calculate B and C first. Again, we use the first row to time the first column, the first row to time the second column, and we can get this big matrix. And then we use the matrix A to do matrix multiplication with the big matrix. And again, it's use the first row to time the first column, first row to time the second column. So we can get the huge matrix here, and we denote it as D2. And now we can observe that D1 and D2 are actually the same. So by doing the calculation, we already verify that the key point we mentioned in the last page is correct. Now we are going to see another properties. You can see that in this page, we focus on question C and question D. Again, we denote it as A, B, and C. So question C is actually says we want to calculate B at C first, then do the matrix multiplication. And for question D, actually it says A times B first and A times C. Then we add them together, whether these two are equivalent. And of course, the key point tells us these two are equivalent, and we are going to see how to verify it. On this page, we do the calculation again. You may think it looks complex, but actually it's easy to follow. Again, we do the element-wise addition. In the brackets, we add B11, C11, B12, C12, and in this way, we get this matrix. Then we do the matrix multiplication. We can see the first row times the first column, then first row times the second column, and finally, we get the answer. We denote it as D1. Then in question D, we do the matrix multiplication separately first. Again, we do A times B, first row, first column, to get this one. Then first row, second column, to get this one. And it's A times C, first row, first column, this one. I think you already know how to do it. So we skip this step and get the final answer. It's D2. And we make the observation again. That means D1 equivalent to D2. So in this way, I think we already verified the key point is right again. So now we have two properties when we do the matrix multiplication. And I think if you can use these two properties very familiar, you will find sometimes it will be much easier to do the matrix calculation. The proof of the key point is very easy, and I think if you are interested in it, you can do the derivation yourself after tutorial. And now we go to question 5. Question 5's topic is about multiplication by a scalar. And actually, I think question 5 and question 4 talk about the same topic, because you can see if we have a matrix A of size m times n, if we set m equals to 1 and n equals to 1, this is actually a scalar, since it only has one row and one element. So what is satisfied in question 4 is also satisfied in question 5. We only need to change the matrix in Scalar. The proof is actually the same. You can see that we can regard lambda as a matrix of size 1 times 1, and this is also can be regarded as a matrix of size 1 times 1. So I will now spend more time to talk about question 5, and we can have a quick look at question 5. That question A and question B are exactly the same. The difference is that in question A, we calculate 3 times 2 first. However, in question B, we calculate 3 times the matrix first. Then we go to question C and question D. again, we can see that actually question C calculates 3 add 2 first, and question D calculates the multiplication separately first. Then for question E and F, it's the same. So if you meet some questions in this way, you can only calculate part of them and get the answer from another part. Now we go to the last question. Oh, about question 5. If you want the solutions for the 6 questions, you can check the Moodle after the tutorial. We will show details about the solutions. And now we move to question 6. It talks about the systems of linear equations. I think Dr. Wang have not talked much about how to use matrices to solve the problem of system of linear equations. And in this question, I only want you to have a feeling about we can use matrix to represent linear equations. And there is a linkage between the matrices and the linear equations. And actually, there are some students asked how exactly we can use the matrices to solve the linear equations. I want to say that there are various methods like Gaussian, like calculate the inverse and the matrix transformation. We can choose different methods according to different cases. And there is a student asked a question how we can actually use matrix to save question 6. But since time is limited, I cannot write details on the screen. So if you also want to know how we exactly use matrices to solve the system of linear equations, you can tap your emails on the screen. I will contact you personally. Or you can wait Dr. Wang to tell you how to use different methods to solve the equations. Now we come to question 6. Actually, question 6 can divide it into 2 parts. The first part is to solve the linear equations, and the second part is to do a simple matrix multiplication. And now we go to the next page to see the details. For question 6, this is the solutions for the first part. However, this is a solution in a high school way that we do not need to use the knowledge from the college. So I only show this to show you that whatever you can solve this problem. And now we focus on this part, that we have the solutions after the high school way. And we got the answer x1 equals to 2, and x2 equals to minus 3, and x3 equals to 1. And now we go to the second part of the question. We can see that we have a question, we have a matrix that its first column is actually the coefficients before variable x1. And the second row, second column is actually the coefficients before the variable x2. And for the third column, it's actually the coefficients before the x3. And for this vector, it's actually the solutions. This is x1, this is x2, this is x3. And now we are going to see what will happen. The calculation is easy. We use the first row to do the dot product with the vector and get the answer minus 9. And the second row to do the dot product to get the answer 14. Then the third row and the third and to do the dot product with the vector to get the answer minus 10. Then we can observe that this is actually the answer on the right side of the equation. So after these 2 questions, I hope you can bear in mind that we can use matrices to solve the linear equations. And there is a close linkage between the matrices and the linear equations. This is 6 questions for tutorial 1. And on the final page, we have a brief summary. For the summary, we can see that today we have talked about 4 points. The first point is the matrix addition. And in this point, we have 3 key points. The first one is we need to check the dimensions. The second is we need to do the addition by element-wise way. And the third is that if there is a scalar, we need to do the multiplication between the scalar and every element in the matrix. And the second is the matrix multiplication. Again, we need to check the size and predict the size of the final result and know exactly how to do the calculation. And we have learned a special case. It's about the identity matrix. If we have found matrix in the same way, we do not need to do the regular calculation. We can get the answer directly. And we need to get a feeling of the matrix transformation. If we have an original matrix and we put a matrix on the right side, we actually do the column transformation of the original matrix. And if we have original matrix and we put a matrix on the left side, we are actually doing the row-wise transformation. And then we talk about matrix scalar multiplication properties. And I hope you bear in mind that matrix is a scalar is a matrix of size 1 times 1. And then we go to the system of linear equations. The key point of this part is that I want you to know that there is a linkage between the matrix and the linear equations. And we can use matrix to solve the linear equations. And that's all. Now, if you have any questions, please send me messages or you can unmute your microphone.
Hello, teacher.
Hi.
Okay, so you said scalar is a 1 times 1 matrix.
Yes.
But then if we have a 1 times 1 and then we multiply by a matrix of like 3 times 3, it's not possible. So would you say that scalar is a special type of 1 times 1 matrix?
Yeah, I think you have a good question. Maybe it's not proper to say it's a 1 times 1 matrix, but when we understand the properties, I think it's no problem when we say it's a matrix. But when we do the matrix multiplication, I think we cannot treat the scalar as a small matrix, or our key point 1 is not correct.
I see, thank you. One more question is that if I have like 1 times 2 and then multiply by 2 times 1, then the result will be a 1 times 1 matrix.
Yeah.
And if in this case, does this become a scalar?
Yes, it's a scalar.
I see, thank you very much.
I have a question about question 6.
Question 6, okay.
In the lecture, I think Professor has already explained or talked about how we can solve the linear equation by not using the high school way. And I would like to ask about it as we read about the note, and he is like using the identity matrix to cancel out the coefficient between the x1, x2, x3. And I want to ask about how we can do it, like just about like not using the high school way. Thank you.
I know. Does Dr. Wang solve it in this way?
Yes, something like this, but just 2 times 2 matrix. So in this case, it is a 3 times 3 matrix, and I would like to know how to solve it. Thank you.
Okay, no problem. Can you type your emails on the screen so I can send you the details by email? It seems time consuming to write the questions here. You can send me personally, or you can type your emails directly on the screen. Both are fine.
Hi, I have a question regarding 1 times 1 scalar.
1 times 1 scalar.
Matrix. Yeah. Do we have to use the bracket or no? For
No scalars, no brackets. If we meet the scalars for, we do not need to add brackets here. It is not necessary.
So even though the final answer is a 1 times 1, we do not need to include the bracket, right?
Yes.
Okay, thank you.
Well, I see someone have asked questions about the non-zero solution. Can you give me your email? I think I can explain to you more clear by email. Or you are shy to answer my questions here, I type my email on the screen. You can send me email after the class. Oh, sorry, I should send to everyone. And about the solutions for the tutorials, sorry. And about the solutions to tutorials, we will post it after the reading week, since we want you guys to solve the problems yourself first. But if you have any questions about the solutions and don't want to wait after the reading week, you can send us emails, or you can book a time to come to our office to talk to us face to face. Both are fine for us. It's up to you.
When
Okay.
we upload the answer on the Moodle, about the next page of the answer, of the tutorial.
Okay, for this tutorial, we will put all the answers. But for the questions, for the past tutorial questions, we will not post the answer. We will post the answer after the reading week. Where can we find more questions?
I mean, you have uploaded 2 pages of 1853. You have uploaded 2 pages of tutorial paper.
2
Is
pages?
it right?
Oh, yes.
But I cannot find the solution of another page.
Oh, I see. We will post it on the Moodle later, soon after the tutorial is finished. Where can we find more questions? Do you know you can find the past papers? You can find the past papers in Hong Kong U Library. Or if you want more questions, maybe we can post some reading materials on the Moodle after the tutorial. So for
Can
those,
you explain a little bit about question 6 in the next in another PDF paper?
oh, no problem. I will give you more details about the question 6. Find the course outline. Okay. I will ask Dr. Wang to post it on the Moodle so you guys can check the course outlines. So if you have any questions, don't be shy to type it on the screen. How many examples and when? Sure, no problem. Now, please type your questions about the tutorial questions or any questions about the courses. Both are fine. I will wait a few more minutes. If not, it's time to end the tutorials. Any questions is fine. I will help you to ask Dr. Wang or other tutors.
I have another question.
Okay.
In the lesson, we are taught to make identity matrix to solve questions like questions number 6, right?
Yeah.
Is there any trick to make the identity matrix, or are we supposed to figure it out by ourselves?
Actually, there are some tricks, and if you like to know, you can type your emails on the screen, or you can send me emails after the tutorial. I can send you more about how to use matrix to solve the equation. But actually, I think Dr. Wang will teach you about this in the following lecture.
Okay, thank you.
Now time is up. You can leave the Zoom, or you have any questions, you can still type it on screen. Bye, see you next time.